So velocity is defined by the rate of change of the particle's position. As long as the particle is moving, its position is changing as a function of time. And so in this section, we're going to define three types of variables for the velocity. The first one is the average velocity. The second is the average speed. And finally, the instantaneous velocity. So we'll go through these three types and define in each case what is the variable. So the average velocity is defined by the rate at which the displacement occurs, or in other words, it is the rate at which the position of the particle is changing. And when we say average, we mean that we are looking at a given time interval. So this is why the velocity, the average velocity, is defined by the ratio between the displacement, so how much does the position of the particle change in a given time interval. And so it's nothing else than, so x final minus x initial divided by t final minus t initial. Note that, don't forget that the position, x initial and x final are vectors. Delta x is a vector as well, and v average is a vector. So v average, it shows the rate at which displacement is occurring and in which direction as well, because it has a direction component as a vector. Of course, as you can see, it's measured as in meters per second, because you have in the numerator a meter and then in the denominator seconds from the definition, and so its unit is meters per second. Now, how can we understand this average velocity in a graph? Consider that you have a particle moving from some x initial, some x final. And this graph in here, you have two axes. So it shows the x as a function of time, the position x. How does it change as a function of time? And this is represented in the red curve in here. So let's suppose the particle was at a given position A, its initial position, and it moves up to some other point B, right? Then if you want to draw these 2 points on the graph, then at t initial, you just have to make a projection from the curve to the time axis. And so in this way, you will define how much is the t initial. So at t initial, you know that the particle is at x final, x initial position. And at t final in here, you do the same, you do a projection from the point to the axis. And so you know that the particle is at a given position x final. Now, have a look. The difference between these two vertical lines, this defines the time interval, because it's nothing else than t final minus t initial. And the difference between these two horizontal lines is nothing else than x final minus x initial, which is delta x. And from here, you can see that this delta x over t, delta t, it's nothing else than the slope of the line that is drawn from point A to point B, or between points A and B. And so from here, we can deduce that the average velocity, by definition, it's the slope of the line that connects the two positions, initial and final, in a position time graph. So this graph, we call it position time graph because it's a position as a function of time. So this is for the average velocity. Now we have another variable, or another mathematical object to use, which is the average speed. Mathematical definition of the velocity. What is the average speed? The average speed actually is a total distance traveled by a given object divided by the total time interval required to travel that distance. So suppose that the object has moved between an initial time ti and the final time tf, a given distance d, then you can define what we call the average speed as the ratio between the distance and the time in this way. So it's d over delta t, where d is the distance, as we have seen earlier, and the average speed we actually denoted in this way. So it's a dot s dot. Now we have to specify a few properties of this new variable. First of all, the speed is a scalar quantity, which means that it's a number and it has no direction because it's not a vector. the speed is always expressed as a positive number, because as you can see from the ratio in here, so the distance is a positive number. It's a scalar quantity as well. And delta t, which is the time, is also all the time positive, because time increases and you don't have a decreasing time. So since d and delta t are both positive, then the average speed is also positive. And finally, the average speed is not the magnitude of the average velocity. So d, because d is different than delta x, we have seen earlier that the distance is not necessarily the magnitude of the delta x vector. It could be equal in particular case, but it's not a general case. And so since d is different than delta x, then it's obvious that the average speed would be different than the average velocity, because the average speed is defined as a function of the distance, while the average velocity is defined as a function of delta x. So let's actually just illustrate this with an example. Consider this case where you have a car, okay, at a given point. And so this car is at t initial, it is at x initial. If we just locate its position with respect to a given origin point along a given x-axis. So let's suppose that this car will make a turnaround. So it's just gonna go through a circular path, and it's like you can see here on this red dotted or dashed curve. So at time t1, it will be at this position. It will go through this circular path. At a given time tn, it will be arrived this position. And finally, at the time t final, so the last time in this time interval we are looking at, it will arrive to this position, which is x final. But notice that x initial and x final, they are the same. So the car, it travels from a given point along a circular path, and it gets back to this initial point, this initial position. So in this case, x final is equal to x initial, which means that delta x, which is defined as x final minus x initial, is equal to 0. And that means that the average velocity defined by the ratio between delta x and delta t is also equal to 0. However, what about the average speed in this case? Let's have a look. So the average speed, as we have seen here, is defined as the ratio between the distance traveled by the object and the time interval. And here, if you just have a look, the car between time t initial and time t final, it has traveled the circumference of this circular path. So the distance traveled by the particle is different than 0, even though x initial is equal to x final. And that means that obviously the average speed is different than 0. So this is an example which shows that the average speed is different than the magnitude of the average velocity vector. And this is a consequence of the fact that the distance is different than the magnitude of the displacement vector. It could be the case that average speed is equal to the average velocity, but they are just particular cases and not general. Now, we have defined the velocity, both average velocity and the average speed in a given time interval. Now, what about the velocity at a given point? So what if we have a particle moving in a given direction, and we want to define, or we want to measure its velocity at a given time? So what does it mean, this? The instantaneous velocity, in few words, it indicates what is happening at every point of time. And we are going to try to define it on the basis of an average velocity. In other words, we have seen that the average velocity, we can define it graphically as the slope of this line, which connects the two positions, initial and final, in a position time graph, right? Now, if we are talking about instantaneous velocity, that means that we're talking about a given point, right? So what we are going to do on this graph, we're going to get this point B as close as possible to the point A, such that at some point we'll arrive to point A. And that means that we are going to reduce the time interval, delta t, so that we get as close as possible to the point A, so that at some point there will be no time interval, so delta t would be equal to 0. We'll be talking about an infinitesimal time interval, which is the dt. Actually, it's in other words the time at which we are at the given position in A. So that's what we do here. If we move along this red curve, okay, then in this way we are, getting closer and closer to the point A, up to the point where we are sitting on the point A, because this is the point where we want to determine the instantaneous velocity. And that, in other words, means that as a function of time, you are reducing the time interval. If you are at point B, your time interval is the longest, actually, vector in here. And as long as you get close to A, this time interval reduces more and more up to the point where we are at the point A. So as delta t gets smaller, the blue line approaches more and more the green line. And you can see that the green line, so when you approach more and more to the point A, your blue line becomes the green line. And as you can see just from the graph, that the green line is nothing else than the tangent to the graph at point A. Okay. Now, we can deduce from this that the instantaneous velocity is actually the slope of the line tangent to the curve x versus time. Now, how can we define this more mathematically? So in terms of mathematical equation. When we say that we are defining instantaneous velocity on the basis of the average velocity, in other words, we mean that the instantaneous velocity, it's nothing else than the average velocity, but in a very small time interval, or we call it infinitesimal time interval. That means what we have written in here. So this is the average velocity, and we are defining it in a very, very small time interval. So this is why we take the limit of this ratio when delta t goes to 0. And by definition, the limit of delta x over delta t when delta t goes to 0 is nothing else than the first derivative of the position vector x with respect to time. So this is why the instantaneous velocity is the limit of the average velocity as delta t becomes infinitesimally short, or as delta t approaches 0. And the instantaneous velocity, keep in mind, it can be positive, negative, or it could be 0. That depends on the way the x, the position, is changing. So if x, for example, is growing, it's increasing, that means that v is positive, and the same for the other cases. So it could be as well negative and 0. Now, the instantaneous speed, it's also another notation and definition that we have to go through. In this case, in the case of instantaneous variables, the instantaneous speed is defined as the magnitude of the instantaneous velocity. So when we talk about the instantaneous variable, velocity and the speed, the velocity, instantaneous velocity, is the vector that shows the value of the velocity at a given time t and its direction. And the instantaneous speed, it's just the value of the velocity. So this is why it's the magnitude of the instantaneous velocity. So this is it for the velocity. Now we will move on with the acceleration. So in the same way we have defined the velocity, and we have said that we have two kind of variables, the average velocity and the instantaneous velocity. We are going to define the acceleration also in two kinds of variables. So we will have the average acceleration and the instantaneous acceleration. Let's start with the acceleration. What is the acceleration? If we are going to define it, it's the rate at which the velocity is changing. Now, if we're talking about average acceleration, that means we are looking at a given time interval. And this is why the average acceleration, it's defined as the ratio between delta v and delta t. So how much the velocity is changing during a given time interval delta t. So it's v final minus v initial divided by t final minus t initial. Now note that VI and VF, they are the values of the instantaneous velocity evaluated at time t initial and t final, right? So this V that appear in here, the two, okay, this is nothing else than the instantaneous velocity evaluated at the time tf, and this is the instantaneous velocity evaluated at the time ti. And as you can see from the definition, that you have on the numerator meters per second, and in the denominator you have second. So this is why A is measured in terms of meters per second squared in the SI units. So this is it for the average acceleration. Now, if we move on to the instantaneous acceleration, here we are going to use the same reasoning as we did for the velocity. So it's nothing else than the limit of the average acceleration as the time interval approaches 0. So it becomes infinitesimally short. And so this is why we write down A as equal to the limit of delta V over delta T when delta T goes to 0. So this is nothing else than the derivative of the velocity vector with respect to time. And if we replace in here, so this is the first expression. Now, if you replace V with its definition, as you can see in here, so this is it here. It's the derivative of x with respect to time. If you just put this, substitute V with dx dt, then you will end up with d squared x over dt squared. So you can define the acceleration either as the first derivative of the velocity with respect to time, or as the second derivative of the position with respect to time. So both these expressions, they can be used, either this one or this one. Depends on what you have in the given. So if you have x, then you would use d squared x dt squared. If you know what is v, then you can use dv dt. And note that also the acceleration is a vector. So it shows the rate at which the velocity is changing and in which direction as well. So don't forget that all the variables which are written here, they are vectors. We just don't have the vector notation because we are in the one-dimensional case. So we know very well the direction in which the particle is moving. And so we just omit the vector notation here. But don't forget that they are all vectors. Now, again, if you just have a look here at the graph, so we want to see the acceleration in a graph or velocity versus time graph. So here you have the velocity as a function of time. How does it change? The velocity as a function of time. And the way it changes is described by this red curve in here. Now, if you just take 2 points to be the initial and the final positions, like the A and B, you just make the projection along the V and the T axis. So you could specify T initial, T final, and V initial and V final. You will see at the end that the average acceleration, which is defined in a given time interval, is nothing else than the slope of the line, right, that connects A to B, because the slope of this line is just delta V over delta T, and this is the average velocity. And we can also conclude that the slope of the green line at a given point is nothing else than the instantaneous acceleration. So also for the acceleration, we can define all the variables, whether average acceleration or instantaneous acceleration on a graph. Now let's talk a little bit about the acceleration and the deceleration. How to know when the object is accelerating and when the object is decelerating. So when an object's velocity and acceleration are in the same direction, they are both pointing in the same direction, then we can say that the object is speeding up. Like if you take these two cases, we have a car and you have a van. Okay, doesn't matter in which direction the object is moving. You just have to look at the velocity vector and the acceleration vector. If both vectors, they are pointing in the same direction, that means that the velocity is increasing as a function of time because you are adding this vector to V, and that means that the particle or the object is accelerating. And the same for the van in here. So for the van, V and A, they are both pointing in the same direction, which means that V increases as a function of time, and that means that the object is accelerating. Now, When an object's velocity and acceleration are in opposite directions, then this means that the object is slowing down, as we can have, or we can see here clearly in this example. So this van as well, it is moving in one direction, and this is its vector velocity. However, its acceleration is in the opposite direction with respect to the velocity. And in this case, that means the velocity is decreasing as a function of time, because the acceleration vector is opposing to v, and it means that the object is decelerating or slowing down. So whenever you want to check whether your object is accelerating or decelerating, you have to have a look at these two vectors. Now we are going to move on with the first model, actually, which is a particle under constant acceleration. And here we are going to derive the set of equations that describe uniformly accelerated rectilinear motion. And we're going to relate the following variables actually with each other. So we are going to find the equations that relate the velocity and the time, the position and the time, the velocity and the displacement. So in this case, v function of x, and the position versus the velocity and the time. So what is the equation that relates the position, the velocity, and the time together? So here we start. First of all, let's start with the first equation, which is velocity as a function of time. Now, we have a particle which is moving under constant acceleration a, right? And we know what is the definition of the acceleration. So we know that the acceleration a, by definition, is the derivative of the velocity with respect to time, right? Since the acceleration is constant, that means that at any time, the instantaneous acceleration is equal to the same value. And so we can use this definition and conclude that the differential in v is equal to a times differential in time. So here we have one variable, which is the velocity. Here you have the other variable, which is the time. And you know that your variable a is constant. So you take the integration on the two sides of the equation, you end up with integral dv equals to integral a dt. But since a is a constant, then you can put it out of the integral, right? You can get it out of the integral, and you can just now make the integral for both the velocity and the time between a given time range. So if we assume that at time t0, here you have integral of dv between t0 and t, then you would end up with the integral of dv is simply v. So it's like the integral of dx is x, right? It's the same. And the integral of dt is t. So now if you just evaluate these two functions, v and t, at the time t0 and t, you would end up with the following equation. So here, v at the time t minus v at the time t0 is equal to a times t minus t0. Now, most of the cases we take usually t0 to be equal to 0, and we denote the velocity at the time t0, t initial is equal to v0. So from here we can deduce that if we have a particle moving under constant acceleration, its velocity at any time t is equal to its initial velocity v0 plus a times t, where a is just a constant. The second kinematic equation of interest is the position as a function of time. So how to get the equation of the position? Actually, we start from the definition of the velocity v, because now we know what is the velocity. We know that the acceleration a is equal to constant, and we know that the velocity is a function of time, and it is equal to v0 plus at. So we start from here, and then we use the definition of the instantaneous velocity, which is the derivative of the position with respect to time in here. So that means we can write down differential in x dx as equal to v times dt, right? And all what we need to do now is to replace v by its expression. So this is why we replace v by v0 plus at. And then we make the integration on both sides of the equation. So we end up with, here we just have to make the expansion. So it's integral of v0 dt. we can get out the v0 of the integral because it's simply a constant. It does not have any role in the integral, plus a times t times dt. But since a is also a constant, we can get it out of the integral. And so we end up with integral of dx, okay, is equal to v0 integral dt plus a times integral t dt. And we can apply the time limits of the integral for all of them between time t0, the initial time, and the time t. Now, all what we need to do now is the integration. So we know the integral of dx is simply x. The integral of t dt is simply t. And the integral of t dt is 1 over 2t squared. So it's half t squared. So we just replace each integral by its expression. And now we need to make the evaluation of the function that we get between the limits of the integral, so between t0 and t. So we end up with xt minus xt0 is equal to v0 times t minus t0 plus 1 over 2 times a, which is a constant, times t squared minus t0 squared. So this is the general expression that we have out of this integral. Now, if we take t0 to be equal to 0, and we replace x at the time t0, evaluated at the time t0 by x0, then we can simplify a little bit the form of this equation and write down x at a given time t. It can be evaluated as the summation between x0 and v0t and half at squared. And so in this way, we can see that we have actually written an equation x as a function only of time, because v0, a, and x0, they are just constants. Now we continue with another equation of interest, which is the equation that relates or connects v to x. So this is the velocity as a function of x. Actually, we can show this equation, or we can determine or derive this equation by using the definition of the variables that we have. So we have two definitions, basically. We have the definition of the acceleration, where we have the velocity and the time, and we have the definition of the velocity v, where we have the position and the time. Now, we are looking for a equation that relates v to x, which means that there is no time explicitly in this equation. This is why we're going to eliminate the time in these two equations and get an equation which is only function of v and x. So let's do this. From the first equation here, we can write down dt is equal to dv over a. And if we replace dt by this expression in the definition of the velocity v, we end up with v equals dx over, instead of dt, we will put dv over a. So that is equal to a times dx over dv. And so now all what we can do is just to make the, to collect the same variables on the same side of the equation and then make the integration. So we end up with v times dv equals to a times dx. And now we just do the integration between the initial and the final time. So the integral of v dv is equal to half v squared. On the right-hand side of the equation, a is a constant. We can get it out of the integral, and the integral of the x is simply x. And so if you just do the integration, you will end up with 1 over 2 half v at the time t squared minus v at the time t0 squared, which we denote by v0 here, is equal to a times x at the time t minus x at the time t0, or in other words, x0. And from here, you could see that we can write down the equation v squared minus v0 squared is equal to 2 times a times x minus x0, where x0 and v0 are the values of the position and the velocity at the initial time, and x and v, they are the position and the velocity provided or given at time t, at a particular time t. So this is it for this kinematic equation. We have one summary in here for the kinematic equations for the case where we have a particle or an object moving under constant acceleration. So please note that these equations then can be used in the problems without proof. So you just, all what you need to know are these equations, which are in the black and in the blue boxes. You can take them and apply them immediately in the problems without really showing, without going through all these proof. But you have to know how to prove them, right? And you have to know that the derivation of the equations using the integrals is requested, because they may ask you to calculate the velocity or the acceleration of a given particle if you know its position vector, for example. So you need to know, to understand and to know how to derive them, but in the problems you can immediately use them. So here, as you can see, we have those three equations, which are the velocity as a function of time, we have the position as a function of time, and we have the velocity as a function of the position. Now, there is another equation, a fourth equation, which gives the position as a function of the velocity and the time, which can be written like this. So x is equal to x0 plus half v plus v0 multiplied by t. We did not show this equation. We can actually make a reasoning to understand it, but usually this equation is not very much used. The most used equations in the problem, they are those in this red box. So we are going to continue with the free falling objects.